Hi, and this is your lecture video for Chapter 2, Section 2. This section refers to units of measurement. We've already done an activity in class dealing with one particular unit specifically, that's density. And we're going to expand our understanding of units during this section. So a few learning goals that we have for you, or I have for you, State of California has for you, for this section. First thing, I want you to be able to distinguish between a quantity, a unit, and a measurement standard. I would like you to be able to name SI units for length, mass, time, volume, and density. I would like you to be able to distinguish between mass and weight. That is actually going to be our quick write prompt for this section. You're going to need to be able to perform density calculations. You'll also need to be able to transform a statement of equality into a conversion factor. And this is what you're going to need to be able to do in order to complete the units conversion assignment that I've already handed out in class. Alright, so a measurement. What is a measurement? A measurement is something that you do every day. It's something that you do every time that you measure your height, every time that you read your watch, every time that you take your temperature, every time that you weigh a cantaloupe. These are all measurements. Now, specifically in chemistry, we measure quantities. We measure quantities when we do experiments, when we calculate results, whenever we use numbers to report any sort of measurement, or compare our results to standards. In any particular measurement, we use a measuring tool to compare some dimension of an object to a standard. Here, we have the thickness of a skin fold at the waist is being measured using calipers. This is one of the more accurate ways of measuring body fat. It seems kind of old-fashioned, but it's still one of the most accurate ways to do so. So when we are stating a measurement, right, we've taken the measurement, we have that information, but we need to communicate it in order for it to be useful. We need to say a number followed by a unit. And this is every time. We need to create a habit in which anytime we communicate a measurement, we follow it up by a unit. That's going to involve us being familiar with what we're saying before we actually say it. It is a good practice in general. So, for example, let's look at these numbers I have here. We have a number and a unit. We have 35 meters. We have 0.25 liters. We have 225 pounds. We have 3.4 hours. Notice that neither the number nor the unit hold significant meaning without the other. But once you pair them, you're able to communicate something meaningful. So there are systems for these units that standardize them. Before these systems came around, for example, a foot was literally defined as the length of the king's foot. So you can imagine the difficulties therein. Every time a new king came into power, the size of his foot would change. Therefore, the size of a foot would change. Obviously has some hardships that come along with it, so a standardized system is a good idea. The standardized systems that we use today are the metric system or the international system, the SI system. The reason it's SI and not IS is because the international system is actually named in French, and so you use the international actually comes second. But the international system and the metric system are both based on 10. The number 10, as well, it's why it's very useful. It's very easy to communicate information because it's based on that round whole number. It's the most common system used in the world. The United States commonly does not use this system. However, it is the officially adopted system of the United States, even though it's not commonly used. It's becoming more common in use as it is kind of like faded into the education system. But things like Fahrenheit and the yard and the foot are still the most common units used in speech. But in terms of science, it is definitely the international system that's going to be used. You will not hear scientists use the word foot. In fact, when I was in 8th grade, my science teacher kind of pulled one over on my class when I was in 7th grade. We came in, we sat down, he said, "Hello, welcome to 7th grade. This is what we're going to do for science. Can anyone think of a 4-letter word that starts with F that I never want to hear come out of your mouth?" So obviously we were all thinking of the different curse words that we knew. But obviously we didn't want to get in trouble, say them, so we didn't. And finally he let the cat out of the bag that he meant foot. Right? It was kind of a funny thing, but scientists truly do not use that 4-letter word. The units that we'll find in the metric system and the SI system try to help define certain quantities. Those quantities are length, volume, mass, temperature, and time. Those are the standard SI measurements. You can derive other measurements, other units from these basic units, but the ones I have listed here are the standard ones. In the metric system, we have meters, liters, grams, seconds, and degrees Celsius. The SI system is a little bit different. We still have meters for length, but for volume we have cubic meters. For mass we have kilograms instead of grams. We still have seconds for time, but for temperature we have the Kelvin scale. Length, I'm going to blow through these pretty quickly. Length is used in both SI systems. You can see that we have a statement of equality, which I'll talk about later. 1 meter is 39.4 inches, so we can convert between one or the other. Inches and centimeters, similarly, we can convert between those. 1 inch is exactly, actually it's not even an approximation, is exactly 2.54 centimeters. You can also use that statement of equality to create a conversion factor. Volume is defined as the space occupied by anything. All right. One of the common units that you'll use to describe volume is liters. Now, obviously, we can put different prefixes on that to denote how large a scale we're speaking, but liters is very common. We also have in America a unit called the quart that is very, very close to 1 liter, but is not quite. In the SI system, instead of liters, they use cubic meters. That's actually a pretty darn big volume if we get a chance to demonstrate that in class. The mass of an object is the quantity of matter it contains. When we're on the surface of Earth, we can measure this using a spring scale. It's more accurately used or measured using a balance. In the metric system, we use grams. In the SI system, we use kilograms. But I do want to highlight the difference between weight and mass here. Again, this is going to be something that you complete a quick write on. Mass is the quantity of matter. How much stuff is there? How much space it takes up? You're measuring it with a balance, and the unit's going to be kilograms. Weight, however, is the force. That's a capital F. Force of gravity pulling on that matter. Okay, it's the force of gravity pulling on that matter. So the more gravity, the more force is pulling on that matter. The matter hasn't changed, but the force has. Therefore, the weight will increase. You can measure weight with a spring scale. It has a completely different unit. It's called a Newton. When you guys move on to physics, you'll become a little bit more familiar with that. And for example, on the moon, our mass will be the exact same because we're still made of the same stuff, but our weight will be less because the gravitational force on the moon is significantly less. Temperature, there are going to be 2 different scales that we use in this class. One is the Celsius scale, one is the Kelvin scale. We denote those by degrees Celsius and then Kelvin. We're going to use time in this class. The unit that we will use in this class is seconds. We do not commonly use hours. We do not commonly use days. It's going to be most significantly seconds. If you have some spare time, you're interested in how we define a second, you can Google search or YouTube search the atomic clock. It actually the atomic clock is a machine that measures the number of pulses or oscillations coming from a cesium atom, which is a very regular number of pulses. Yeah, I just added that because I find it interesting. We do have the standard units, but we also have derived units. Notice that these derived units are simply base units that have some sort of math involved. You can see with the volume, you have those meters, but now they're cubed. For density, you have a kilogram and you have a meter, but you're dividing them and then cubing them. We have speed is the meter and the second, but you're dividing them. The Newton, we have some multiplication between the meter and the kilogram. We have dividing by seconds squared, and energy and pressure also there. But you can see that all these derived units have base units involved with some sort of mathematical function. Volume is going to be something that we talk about in this class fairly significantly, especially when we get to the gas unit. There are different units for volume. We can use the cubic meters base, and we can add some prefixes to change the scale in which we're talking. Centimeters cubed, decimeters cubed. Those are both completely legitimate, all three are completely legitimate units, as well as the liter and the milliliter. And we can move between these two types of units because it's very lucky that 1 centimeter cubed is the exact same volume as 1 milliliter cubed. That's going to be a statement of equality that we use a lot in this class. Density is one of those derived units. We talked about this in our penny density lab. It's the amount of mass per unit of volume of that stuff. Right? The SI unit is kilograms per meter cubed. The common unit that we are going to use in our class is grams per cubic centimeter or grams per milliliter. They're the exact same thing. We have some examples. We have steel compared to wood compared to air. You take 1 cubic meter of each of those materials and take the mass inside of that cubic centimeter. The steel is going to have significantly more mass compared to the wood, which is still going to have significantly more mass compared to air. Now, they take up the same volume, but you're being compared to a much larger mass. And so steel has a significantly larger density than wood, which still has a significantly larger density than air. This is something I'd like you to do. I have a problem for you. I'd like you to practice calculating densities. All right, density is equal to mass divided by volume. I want you to try that out here. So lead has a mass of 22.7 grams. This is a particular sample. It's been massed. It has 22.7 grams. It also has a volume of 2.00 cubic centimeters. I want you to calculate the density. If you need to pause the video, do that now. Your hints here are I've identified the mass as 22.7 grams, the volume as 2.00 cubic centimeters, and because density is equal to mass divided by volume, we simply divide 22.7 grams by 2.00 cubic centimeters to yield 11.4 grams per cubic centimeter. So here's a chart, again, describing quantities and the units that are associated with those quantities: mass, length, volume, temperature, and time. The statements of equality over on the right-hand side of the table are going to be fairly important for us. You're not going to have to memorize those on any particular test. If you need to use those, you'll be given the statements of equality. What you'll have to learn is what to do with the statements of equality. This is a chart describing all of the different prefixes you can throw on a particular unit to change the scale in which you're talking. If you have 1 meter, you can change that to centimeters. Right? There are 100 centimeters in 1 meter. You can also convert that to milliliters. Right? Millimeters. There are going to be 1,000 meters and 1,000 millimeters in 1 meter. Or micrometers. There is going to be 1 million micrometers in 1 meter, and on and on and on. There are going to be some common prefixes that you'll need to memorize just to make yourself functional. Those would include milli, centi, deci, and kilo. All right? Things like micro and nano and mega, we will use periodically, not very commonly, but we will use them periodically. But I will give those statements of equality to you when you need them. All right, here's another opportunity to check how you're doing. I want you to pause the video and see if you can answer this set of questions. For each of the following, indicate whether the unit describes length, mass, or volume. Please pause the video now and complete these problems. All right, see how you did. A bag of tomatoes that is 4.6 kilograms. That's mass. Kilograms represents mass. A person is 2 meters tall. That is length. A medication contains 0.5 grams of aspirin. Again, that is mass. Grams are mass. And then a bottle contains 1.5 liters of water. That is a volume. This is another set of problems I'd like you to attempt. Identify the measurement that has an SI unit, specifically, SI unit. All right. Please pause the video now and complete these problems. You're just going to select one of the options. Let's see how you did. Meters are an SI unit. Seconds are an SI unit. Kilograms are the SI unit, as opposed to grams from the metric system. And then in SI, the SI system, temperature is on the Kelvin scale. All right, conversion factors. This is going to be a huge deal moving forward in this class. A conversion factor is a ratio derived from the equality between two different units that can be used to convert from one to the other. For example, 4 quarters is equal to $1. We all know that. But we can set this up as a statement of equality by putting 4 quarters as a numerator and $1 as a denominator. Carrying out that division, you will equal 1 because the quantities are the same. 4 quarters is the same thing as $1. They're the same value even though they have different units. Similarly, you can flip the denominator and numerator and you'll still have a statement of equality. They'll still equal 1 because they are the same thing. $1 is equal to 4 quarters. Similarly, $0.25, a quarter of a dollar, is equal to 1 quarter. So dividing $0.25 by 1 quarter equals 1. This is what we mean by statement of equality becoming a conversion factor. Now, what I'm going to do here is I'm going to show you an example of how to set up a conversion factor to convert from one unit to another. So we're going to convert 5 kilometers into meters. So we're going from kilometers to meters. So here we have 5 kilometers, and I'm using my statement of equality. 1 kilometer is equal to 1,000 meters. All right? Meters being the new unit, okay, the unit I want to go to. Kilometers being the old unit, the one that I want to move away from. All right? I want to convert from kilometers to meters. The kilometers are the old unit. Meters are the new unit. Now, the reason that I will always be confident that my old unit needs to go on bottom, because as I multiply these terms through, because I have the same unit on the numerator and the denominator, I get to cancel them. All right? I no longer have to carry those throughout the calculation, And to boot, I get to keep the unit that is on the numerator. So now I have successfully gotten rid of the kilometer unit, and the only unit I'll have left is the meter unit. So I've successfully converted from kilometers to meters. Now all that's left is to carry out the numerical part of the calculation, multiplying 5 by 1,000 and dividing by 1. All right, so I'm going to carry over my unit. That's the first most important thing that allows me to know that I'm correct. And then I carry out the numerical calculation, which equals 5,000. So there are 5,000 meters in 5 kilometers. Now I'd like you to pause the video and attempt to convert 7,000 meters into kilometers. Please pause the video now. All right, we're given 7,000 meters. I'm going to multiply by a conversion factor. I'm going to use the statement of equality that 1 kilometer is equal to 1,000 meters. Now, this is the same statement of equality we used in the previous example, but you can see here that I've flipped the units so that kilometers, a kilometer unit is on the numerator and the meter unit is on the denominator. Now, the reason I know I need to do this is because I need that meter from the original value, the 7,000 meters. I need the meters to cancel out. So in order to do that, I have to have meters on the numerator and on the denominator so that they can cancel out once I divide through. Once I do that, the only unit I have left in the equation, or in the calculation, is kilometers. I'm going to bring that over to my answer. That allows me to know that I'm going to be correct once I carry out my numerical calculation, be 7,000 multiplied by 1 divided by 1,000, which equals 7. So there are 7 kilometers in 7,000 meters. All right, that's the end of this video lecture. Sorry it was a long one, but just to recap, I want at the end of this section, I want you to be able to distinguish between a quantity, a unit, and a measurement standard. I want you to be able to name SI units for length, mass, time, volume, and density. I want you to be able to distinguish between mass and weight. Again, there'll be a quick write on that. I want you to be able to perform density calculations as well as transform a statement of equality into a conversion factor. All right, I'll see you guys next period.